Now we turn to the operations. We will look at insert, extract max, and build heap. The first operation is insert, also called bubble up. We append the new value at the end, then swap it upward while it is bigger than its parent. The cost is big, O of log n. The second is extract max, also called heapify-down. We take the root, refill from the last slot, then sift that value down. The cost is again big, O of log n. The third is build-heap. We heapify every internal node from the last one back to the root. The cost is big, O of n. All three use the same repair idea. We sift a value until heap order holds. Insert sifts up. Extract max and build heap both sift down, just from different starting points. To insert a value v, we do two things. We put it at the end, then we bubble it up. Let's see why that is enough. We place v at a at index n, the first free slot. Placing it at the end never breaks completeness. The array stays dense. But it can break heap order. The new leaf may be bigger than its parent. So we bubble up. We swap v upward, one level per comparison, until it is not bigger than its parent or it reaches the root. Each swap moves v up exactly one level. A complete tree of n nodes has height floor of log base 2 of n, so bubble up makes at most big O of log n swaps. Predict first before we trace it. Insert 50 into the 6-node heap 16, 14, 10, 8, 7, 9. 50 is bigger than everything already there. Part A, how many swaps does it make before it settles? Part B, where does it end up? Pause and answer. Here is the answer, 2 swaps. 50 goes to index 6, swaps past its parent 10, then swaps past 16, and it stops at the root, index 0. Notice the point. Even the largest possible value climbs only floor of log base 2 of 7, which is 2 levels, never all 6. That bound is what matters. This is insert in pseudocode. It is 0 indexed in the CLRS style. Let's read it together. First we grow n by 1. Then we write the new key at a at index n-1, the first free slot. We set I to n-1, so I is the position of the new value. The while loop runs while I is greater than 0, and the parent is smaller than a at index I inside the loop. We exchange a at index I with its parent, then set I to the parent index. The value climbs one level each time. When the loop ends, we return n, the new size of the heap. Parent of I is I-1, then divide by 2. The loop stops the moment the parent is not smaller, or I reaches the root. Here is our heap of 6 values. On the left is the tree, and on the right is the same heap written as an array. We want to insert 20. The top row is the starting array. As we work, we add one new row per step and keep the old rows, so you can always look up and see what changed. First, we append 20 at A at index 6, the first free slot. That keeps the tree complete. In the new row, index 6 now holds 20, the glowing cell. Parent of 6 is index 2, which holds 10. 10 is less than 20, so we swap. After the swap, 20 climbs to index 2 and 10 drops to index 6. The two glowing cells are the pair we just swapped. Now compare 20 with its new parent, index 0, 16. 16 is less than 20, so we swap again. 20 moves to index 0, the root, and 16 drops to index 2. Now I is 0, so the loop stops. Heap order is restored in just 2 swaps, the height of a 7-node tree. Read the arithmetic back. The parent of 6 is 2, and the parent of 2 is 0. Each glowing pair was 1 swap. The final heap is 20, 14, 16, 8, 7, 9, 10. Every parent beats its children again in 2 swaps, which is the height of a 7-node tree. Now your turn. Starting from the same 6 values, insert 11 instead of 20. How many swaps happen and where does 11 end up? Pause and think. Here is the answer. 11 goes to at index 6. The parent of 6 is index 2, holding 10, and 10 is less than 11, so one swap moves 11 to index 2. Then its parent, index 0, holds 16, which is bigger, so the loop stops. Only one swap this time. 11 beats its first parent, but not the root. This is insert in C. It takes the array A, the current size n, and the key we want to insert. First, we write the key at A at index, and that is the first free slot at the end of the array. We set I to n, and then n increases by 1, so I now holds the position of the new key. The while loop runs while I is greater than 0. In other words, while we are not yet at the root. We compute the parent index. It is I minus 1, then divide by 2. If A at index parent is greater than or equal to at index I, heap order already holds, so we break out of the loop. Otherwise, we swap A at index I with A at index parent. The key climbs 1 level up. We set I to parent, and the loop checks the next level up. When the loop ends, we return the new size n. The time is big O of log, and there is at most 1 swap per level, and a complete tree has height floor of log base 2 of n. The extra space is big, O of 1, so nothing is allocated. The full program is in the heapops file. It compiles clean under the strict warning flags, and it runs clean under the address and undefined behavior sanitizers. The maximum always sits at the root, A at index 0. Removing it leaves a hole right at the top. We fix both invariants in order. First, we save A at index 0. This is the value we return to the caller. Second, we move the last live element, A at index n-1, up into A at index 0. This keeps completeness. Third, we shrink n by 1. Fourth, we heapify down from the root. The value we just moved in is probably too small for the top, so we sift it down until heap order holds again. Step 4 is exactly Max-heapify, the same sifting routine that also powers Build-heap. 1 operation, 2 callers. Predict first. In the heap 20, 14, 16, 8, 7, 9, 10, extract the max. The last leaf 10 moves up to fill the root and then it sifts down. Part A, which child does it swap with? Part B, how many swaps before it stops? Pause here. Here is the answer. It swaps with the larger child, 16, and lands at index 2. There its only child is 9, which is smaller than 10, so it stops. That is 1 swap. The trace on the next slide confirms it. This is Max-heapify, the most important routine in the chapter. It assumes both children are already valid max heaps, and it fixes just the one node I that might break the rule. First, we find the left and right child indices. We start by assuming the largest value is at I itself. If the left child is inside the heap and bigger than the current largest, then largest becomes the left child. We do the same check for the right child. Now largest holds the index of the biggest of the 3. If largest is not equal to I, we swap A at index I with A at index largest. Then we call Max-heapify again on that child, because the subtree we swapped into may now be broken. Left of I is 2 times I plus 1. Right of I is 2 times I plus 2. We check both against n because a node can have 0, 1, or 2 live children. Max-heapify is the one operation every heap uses. This table shows it at 3 levels: the plain idea, the pseudocode, and the C code. Each row is one step of the same move. First, look at node I and its children. A node has up to 2 children. We find the biggest of the 3. In the code, we compare A at index L and A at index R, and we keep the index of the winner in largest. If a child is bigger than node I, we swap that child up into I. Now node I holds the largest value of that little family. And the third step. The swap may have broken the subtree we just moved into, so we keep sifting. In pseudocode, that is a call to max-heapify on largest. In C, it is the same call, max-heapify of A, N, and largest. That single recursive line is what carries the value all the way down to where it fits. And here is why it is big. O of log n each recursive call moves the sift one level deeper, and a complete tree is only floor of log base 2 of n levels tall. That single fact is the source of every big O of log n cost in this chapter. Let's extract the max from this heap. The max is 20, sitting at the root. We save it to return later. Then we take the last element, 10, and move it up into the root. The heap shrinks from 7 down to 6. The starting row on the right shows 10 now at index 0, the glowing cell. 10 is probably too small up there, so we compare it with its 2 children, 14 and 16. 16 is the biggest, so 16 moves up to the root and 10 sinks down to index 2. The 2 glowing cells are the pair we just swapped. 10 still has 1 child left at index 5, so we keep going from index 2. The only child of 10 is 9. 9 is smaller than 10, so we stop. Nothing else moves and 10 settles at index 2. Heap order is back: 16, 14, 10, 8, 7, 9. Every parent beats its children again. A quick check on what that trace guarantees. After extract max finishes is the heap property, meaning both completeness and heap order, guaranteed to be restored. Pause and think. The answer is yes. Moving the last element to the root repairs completeness immediately because the array stays dense. And Max-heapify is proven to repair heap order at the root and at every subtree it recurses into. If it were not restored, the very next extract max could return the wrong value. The pseudocode for extract max is short. It does 3 small chores, then calls Max-heapify to do the real work. First, save A at index 0 into max. That is the value we will return. Then copy the last element, A at index n-1, into the root. Then shrink n by 1, so the old last slot is gone. Now the root may break heap order, so we call Max-heapify on index 0 to sink it back down. Finally, we return max and the new n. Extract max adds no new sifting code. It just repositions the last element and hands the fix to Max-heapify. This is the C version. The function takes the array A and a pointer to the size n. First, we save A at index 0 into max. That is the maximum we will hand back. Then we copy the last element into the root. Its index is the current size -1. Then we shrink the size by 1. The star before n means we change the caller's real size, not a copy of it. Now we call Max-heapify on index 0. It sinks the new root back down to its correct spot. Last, we return max, the value we saved at the start. Extract max costs big O of log and it does 1 sink, with at most 1 swap per level. Peak max is even cheaper. It just reads A at index 0, big O of 1, and changes nothing at all. Think about the size. Extract max on a 1,000,000 element heap touches only about 20 nodes, one path from the root down to a leaf. Not a million. That single short path is the whole win over the big O of nscan we started with. How do we turn a random array into a heap? We call Max-heapify at every internal node, but the order matters. We start at the last internal node and walk backward to the root. The leaves need no work. Any node at index n over 2 or higher is a leaf. A single node is already a tiny valid heap, so we skip them all. The last internal node, the last one that has a child, is at index n over 2 minus 1. That is where we start. We heapify that node, then the one before it, and so on, back to index 0, the root. Going backward has a nice payoff. When we heapify a node, both of its children are already correct heaps. That is exactly what Max-heapify needs to do its job. Now predict. Build-heap calls Max-heapify at about n over 2 nodes, and each call is big, O of log n, so build-heap should be big O of n log n, right? Take a moment. You might say yes, but the answer is no. Build-heap is big. O of n, that big O of log n cost, is a worst case that only the few nodes near the root ever pay. Most nodes sit near the bottom, where heapify sinks just 1 or 2 levels. The next slide adds up the real work. The pseudocode is tiny. One loop, starting at floor of n over 2 minus 1 and counting down to 0. For each index I, it calls Max-heapify. That is the whole of build-heap. It is just one loop over the internal nodes, calling the same Max-heapify we already wrote. No new sifting logic is needed. Let's build a heap from the classic example array. The top row is the starting array, 4, 1, 3, 2, 16, 9, 10, 14, 8, 7. We fix one internal node per row, from the last internal node back to the root. Each row stays so you can see what each call changed. We have 10 elements, so the last internal node is at index n over 2 minus 1, which is 4. We heapify index 4 first. Its value is 16, and its only child is 7. 16 already beats 7, so nothing moves. The glowing cell is just the node we checked. Next is index 3 holding 2. Its children are 14 and 8. 14 is the biggest, so 14 rises to index 3 and 2 sinks to index 7. The two glowing cells are that swap. Now index 2 holding 3. Its children are 9 and 10. 10 is the biggest, so 10 rises to index 2 and 3 sinks to index 6. Now index 1 holding 1. Its biggest child is 16, so 16 rises to index 1 and 1 sinks to index 4. But 1 is still too small there, so it keeps sinking, past 7 down to index 9. 3 cells changed on this one call. Finally, we heapify the root, index 0 holding 4. 4 is too small, so it cascades down through index 1 and index 3, all the way to index 8. Now 16 sits at the root. The array is a valid heap. Every parent is at least as big as its children. Let us read that trace back. The leaves, indices 5 through 9, start out valid, so we begin at the last internal node, index 4, and walk back to the root. The row for I equal to 4 changes nothing, because 16 already beats its child 7. Each later row is one heapify call, and the cells that move show its cascade. The final heap is 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. Every parent is at least as big as its children. This is Build-heap in C. It takes the array A and its size n. If there are fewer than 2 elements, there is nothing to fix, so we return right away. This loop starts at the last internal node, index n over 2 minus 1, and counts down. The trick I minus minus greater than 0 tests I, then decreases it, and it stops cleanly at 0 without wrapping around. For each index I, we call Max-heapify. It is the same routine we already built. The full program is in the code file, and the next slide shows what it prints. Let's run the code. First, we build a heap from the array 4, 1, 3, 2, 16, 9, 10, 14, 8, 7. Then we insert 20 into the heap. Then we print the current max with peak max. Then we extract the max and store it in M. The output starts with the built heap: 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. That matches the trace we just did by hand. After we insert 20, it bubbles up to the front. 20 is now the first value. Peak max reads the front and prints 20. Extract max returns 20 and leaves the heap back at its built state: 16, 14, 10, 8, 7, 9, 3, 2, 4, 1. The output is the same every run. It shows values only, no raw addresses, following the Chapter 1 rule. Notice that extracting the 20 we just added returns the array to its state right after build heap.